Morning, guys. So in yesterday's lesson, we introduced to you Hess's law. Hess's law was basically a statement on energy conservation. It essentially said, as long as we have the same reactants and the same products, regardless whether you take the direct route or regardless if you take an indirect route, as long as we have the same start, same finish, your overall delta H here is actually the same. It was a method that worked. This was the one that gave you a bunch of mini equations. You had a bunch of delta H's for each of the mini steps. We ended up doing some little manipulations. We did things like whenever I needed to scale an equation, let me just write this down here. Whenever you scale an equation, you end up scaling the delta H. So say I doubled the equation, I doubled the delta H. If I end up flipping the equation, if I end up reversing the equation, I switch reactants and products, I end up reversing the sign, right? Changing the sign, another way of saying it. And eventually, because I need to let's take this detour, do step 1, do step 2, step 3, or however many steps here. If I end up adding these equations, I end up just simply adding the delta H's, right? So the method works here. The method, it's a state function. It doesn't matter whether we go from start to finish, whichever method I take. However, it was very tedious. You can imagine having books and books and tables of mini equations. It was already really nice to you because it was giving you first thing is only a couple steps, maybe 2 steps, maybe up to 4 steps or so, but it was giving you the steps that was needed. If you're looking up, like someone gives you an equation, you're looking up tables and tables full of these mini equations. Who knows how many equations you need to do? You need to match up not just for chemicals, you want to make sure all the intermediates and everything cancel out. You want to make sure all the states match up as well. It just becomes a big headache. So what we're going to do in these next 2 lessons here, this is going to be method 4 and tomorrow's lesson method number 5. What we're going to do is we're going to create a formula. And in today's lesson, we're going to call this formula here a formation equation. We're going to talk about what is a formation equation, and then what we're going to do in our data booklet is we're going to tabulate a bunch of what are the enthalpy changes for doing this formation for a handful, about 20, 30 compounds down here. You'll notice better than bond enthalpy, everything was just per bond and just gaseous. For the handful of selected data here, we actually do have some liquids involved, so that's already an advantage of this over the bond enthalpy method. But basically, how do we define formation and utilize these formation numbers? How can we do this part of the math that was easy, right? The simple plus, minus, reverse the sign, scale it, or whatever. And how can we just pretend all these sort of mini equations just sort of canceled out without us having to show all those mini steps? You still need to know how to do that method because that is a sort of question type they can ask you. They can give you a bunch of these mini steps in the mechanism, but these next 2 ways here is going to be a nice shortcut for the 2. So have out table 12 here handy. We're going to come back to it in just a second here. How these 2 lessons are going to be structured upcoming here. We're going to start off looking at, so this is method number 4. We're going to start out looking at defining what this equation is. In this case here, it's going to be defining what is a formation equation, how does it work, and then we're going to come back and we're going to say how does formation provide a shortcut to actually help us find delta H. In the next lesson, we're going to do pretty much a similar format. We're going to do what's called a combustion equation, right? We've seen it before. There's a little technical note we'll touch on, and we'll also come back and we'll say how do combustion numbers actually help us work around the enthalpy cycle. So without further ado here, let's take a look at this formation equation. Make sure you know how to define these equations. So a formation equation is one in which we are looking at the making 1 mole. There's always going to be this little pesky 1 mole in your definitions. We want to be really strict here so that later on if I need to scale it up, if I have 5 moles for the reaction, I can take the value that I know for 1 mole, I can multiply that value pretty simply by 5. So make sure you add that in the definition. A formation equation here is the making 1 mole of whatever species you're talking about, compound, element, what have you. Out of all the chemical ways you can make that chemical, I'm going to choose to make it, they like saying here, from constituent elements. Constituent elements just means the elements that make it up, from the Lego pieces, from the building blocks. And what we're going to do here is we're going to start introducing here at standard state. Because we want to start tabulating some of these numbers here, we want to make a fair comparison between different elements, different compounds, things like that. We want to make sure that everything is at the right reference conditions. That's actually what we've been seeing here as that tiny little naught symbol. I've been hinting at here, delta H here with that naught. That single naught symbol actually refers to standard state, and some things that are required in standard state here, Standard conditions here, technically temperature is not a requirement, but usually we do have it at 25 degrees because we like doing Kelvin here. 25 degrees would be equivalent to 298 Kelvin. So I'm going to tabulate all my values. When I actually go and measure these numbers, everything will at least be 25 degrees. It's not like unfair that one was cold, one was hot. In terms of pressure, standard pressure for the longest time used to be 1 atmosphere. We are under 1 atmosphere of pressure because there's 1 atmosphere above us. We don't really feel it because 1 atmosphere is not all that big. But nowadays we like preferring 1 bar instead. 1 bar is equivalent to, in terms of pascals here, it's 100 kilopascals or 100,000 pascals. That's your standard pressure. If I had solutions, I'd be like saying here 1 mole dm cube, right, dm negative 3, and that in normal we would say 1 molar. Right? So 1 molar is fairly decent, right? We don't need to be overly soluble for us to make 1 molar, but it's a nice constant that we do across the board that will become super important for us in our redox chapter when we start looking at ion concentrations. So I just wanted to define for you what is a formation equation. Notice I haven't talked to you how to get delta H just yet. Just for practice, they might give you examples. Write the formation equation. So write the formation equation. When we actually get to the delta H's, we're going to assume all this is done in the background. I want you to write the formation equation for NaCl, right? So how we're going to do this, super simple. It may feel really easy as well. To make a formation equation, I want to make 1 mole of this compound. That means this NaCl here is supposed to be on the product side, right? Products is what's being produced. We are going to do this at standard state. So under your regular exposure of NaCl, being an ionic compound, you'd expect the lattice to form a solid, right? So it's a high melting point and high boiling point. There's many chemical ways of producing NaCl. We're going to choose the way that starts off just gluing together the elements. What are the elements that make up sodium chloride? Hopefully you're able to say to me here, well, sodium is one of the elements and chlorine is the other element. But again, because we're in standard states, these ones here also have to be in the regular form that we find them in. So sodium has metallic bonding here. Sodium is going to be a solid. Chlorine is unstable as a radical. Chlorine has already paired up. It's become a diatomic when it's an elemental state, but that's a gas there. That's pretty much a formation equation. If this were in any other earlier chapter, you'd say, wait a second, the mass isn't conserved. You would go sort of 2, 1, 2 like that. In this chapter here, because there was this little pesky little 1 mole, it's sort of like trying to rebalance it. For a formation equation, I'm not actually just making NaCl, I am making exactly 1 mole of NaCl. So it's like trying to balance this here with a pesky little 1. Again, we'll see the significance of that in a second here. If we wanted to rebalance this, well, that's okay. It's balancing here is just a ratio, it's just a recipe anyways. If that NaCl has to be a 1, that means I'm stuck with just using 1 NaCl. Chlorine comes to us as a diatomic, we're going to have a half. So here's where we start getting pesky little fractions. Earlier in Hess's law, I didn't want to carry through fractions, but in this case here, sure, having 1 fraction, no problem. Because I want to make a pesky little 1 mole of NaCl, I'm living with that half there. It does not mean we're chopping up Cl2. Cl2 here is still a diatomic like that. It just means by ratio, for every 1 part NaCl, you only need half as much Cl2. If I react, let's say 10 moles of Na, with a half Cl2, I react 5 moles of Cl2. So it's still diatomic, but at least ratio-wise, it is still 2 to 1 to 2. It's just that I write it 1, half, 1. Let's do one other example here. Let's write the formation equation for methanol. Methanol here, under our regular conditions here, is actually a liquid, so pretty easy. We're going to end up creating, there's a pesky little 1 mole. That 1 can't change. We want to make 1 mole of methanol in the liquid state. There's many different chemical ways of making this methanol. We're going to choose to glue together some of these pieces. In fact, this formation equation here can be purely hypothetical. It may be impossible. Maybe the potential energy barriers are too big. Maybe the side reactions react too quickly. But hypothetically, I should be able to take the elements, the building blocks carbon, take hydrogen in its regular form H2, take oxygen in its regular form O2. Hypothetically, I should be able to glue these 3 things together in such a fashion to make methanol. There is that pesky little 1 there, so it's okay to have 1 carbon here. In total, I have 4 H's, so I need a 2 there. I only have 1 O2, so live with it. Okay, fine. Now, 1 half O2 there. Again, because we are in standard state, because there is that little not symbol, 25 degrees and all that, we do want to indicate the state as well. I noticed that already we are diatomics. These are the way they naturally occur. Non-metals, because they only have those weak London forces, so we expect them to be gases. For carbon here, you will very commonly see that as solid, no problem. Back in chapter 4, we saw carbon actually forms multiple allotropes here. It's not possible all the allotropes have the same energy, so we tend to choose the lowest energy state. Unfortunately for us, the lowest energy state for carbon is actually graphite. Cheap pencil lead here, it's not diamond or anything like that. So sometimes you'll see it written carbon solid or carbon graphite. Basically, let's add that to your standard conditions here. Your standard conditions, sure, it implies it has to be pure. It can't be a mixture of things, but it has to be the most stable allotrope. So we've only done allotropes with carbon, but just keep in mind, just because carbon is a solid, we're going to choose the lowest energy form for it. So sometimes question would just be asking you that. Write the formation equation. And all you're going to do is you're going to pretend to make 1 mole of that compound. There's a pesky little 1 that can't change. You're going to choose to do it from the elements in the regular way you see them. You might have the odd fraction. Sometimes you don't. Totally okay. What I'm going to do now is I'm going to pretend I'm going to have done these equations. These could be purely hypothetical. This one here, the formation of NaCl, by doing that equation, I'm going to calculate the enthalpy change of this equation. Because the equation as written is formation, I'm going to call that the enthalpy change of formation to make NaCl. This is the standard enthalpy change of formation to make CH3OH. I wouldn't expect these to be the same. These are totally different chemicals. But just in words here, I'm going to tabulate for you in table 12 a bunch of these values. I'm going to have gone through, maybe through calorimetry, maybe through bond enthalpy, some other method. I found the delta H for doing this reaction. And then what I'm going to do by tabulating these numbers, I'm going to use these numbers to work around the enthalpy cycle. So just in words here, we're going to emphasize that word standard now. So everything is at sort of 1 bar, 1 molar, 25 degrees. This is called the standard. You can call it a heat of formation or standard enthalpy of formation. So in this case here, lots of definitions in this chapter, but again, fortunately, a lot of the definitions have the same structure. So standard, right, we know the 1 bar, 1 molar, and all that, okay? But heat of formation here is the enthalpy change, basically for formation. Later on, we're going to do standard heat of combustion, standard heat of lattice, and all that. The standard heat part doesn't change. It is always going to be enthalpy change. It is going to be this delta H, which is how does your product energy compare to your reactant energy. But the latter part here telling you the type of reaction is just going to be a restatement of what that equation was. So when I defined for you formation earlier, standard heat of formation is the enthalpy change for, and I'm just going to copy out what I did earlier, making 1 mole of your species from the constituent elements, from the Lego pieces that build it up, constituent elements at standard state. So just sort of memorize that structure here. Make sure technically in the definition, make sure you have the 1 mole. Make sure you're able to define, if in this case here I talked about a formation equation, that's this latter part here. Pretend making this chemical from the pure elements. If later on I did standard heat of atomization, it's the enthalpy change for, and you define what's atomization afterwards. Still a pesky little 1 mole, but you just basically restate what you know about that equation. So that's the standard heat of formation. They have gone through and they've tabulated a bunch of these delta HFs. These ones here are on table number 12. We'll scroll to it in just a second here. How does this actually help, right? So we have come up with a new equation. It's called formation. We know at least what formation equation entails. Now what we're going to do is we're going to zoom out, and now we're actually going to consider an enthalpy cycle. We're going to actually utilize these heats of combustion to try to do Hess's law for us, so that somewhere in the background the formation arrows would cancel out, those mini equations would cancel, intermediates, catalysts would cancel out, and all we have to do is just deal with the delta H's. So here's the enthalpy cycle that I want to work with. Let's imagine starting off with reactants. So the reactants have some amount of energy. There is some equation for reactants becoming products. And I want to emphasize here, the equation that I'm interested in, this delta H here is any reaction. I'm going to choose to come up with the formation detour around, but this time here, this equation, the delta H that they're asking for, could be synthesis, it could be redox, it could be neutralization, it could be double decomposition, it could be any type of reaction. To find the delta H of any reaction, what I'm going to do is I'm going to engineer a detour. I'm going to create a pathway to get you from the same start and the same finish, but the detour, the pathway, is actually going to utilize formations. It is possible that the top arrow here itself is also formation, but we're going to find that using this formation detour for a formation equation doesn't work. So it's actually best, in the way I set it up here, I'm just going to emphasize this delta H here is any reaction. It's best that it's not formation. Pretend that I have a bunch of elements that are just sitting beside this. And what I'm going to do, without showing you all the work, what I'm going to do is I'm going to point an arrow from elements. I'm going to look at the compounds on the reactant side, whatever chemicals are making up the particles that are going to collide, and I'm going to pretend to start off with a bunch of these Lego pieces, and I'm going to imagine gluing together all your reactants. The enthalpy change required to do that would be the delta H formation. And just like bond enthalpy, I'm going to specify here reactants, because those are the making of gluing together the reactant side. In a very similar fashion here, if I take the planar elements here, I look at the chemicals on the product side, and I draw an arrow, I can call this energy change here the delta H formation. You'll notice I have a subscript F to remind me of formation, but that's going to be the making of things on the product side, so I'm going to say delta HF prop. In this case here, that's end up forming my enthalpy cycle for me. So just like we did in our Hess's Law lesson yesterday, as long as I have the same start and the same finish, I don't care if you go the direct route, or in this case here, the indirect route, smiley face there, the delta H overall is actually going to be the same both ways. So let me see what we get out of this enthalpy cycle. If you want to find the delta H of any reaction, and I want to really emphasize here, that's the big equation. That one can be any type, decomposition, redox, what have you. If you choose to use the element way of solving it, what you're going to need to do is you're going to need to flip the reactant arrow. When you flip arrows for delta H, we know that endo becomes exo or vice versa. All that's going to happen is we're going to pick up a negative delta HF reactants. Now that we've broken apart them all into elements, I'm just going to follow this arrow. Oh, perfect. This arrow here is pointed the right way. It's pointed towards product. I'm just going to add up all the gluing together and making products. I'm going to end up adding together. Just heat of formation for products. So that's what the enthalpy cycle says. You don't need to ever draw the enthalpy cycle again. Again, lots of definitions and a lot of formulas in this chapter, but luckily for us, the formulas all have the same sort of structure. In fact, I'm going to give you the main way this one here is written out here. I'm still wanting to emphasize here, this is delta H for any equation. We'll do a quick practice shortly. I don't tend to like having a minus and then a plus later on, so I'm just going to put the product term in front. And just in case I may have many different products, right, it produces C and D, I want to glue together what was the energy change to make C and D, and then minus whatever the reactants were. So we're going to have that pesky little sum come back again. This is the enthalpy change formation. We have products minus enthalpy change. There's that not symbol for standard, reactants. This is not on any formula sheet. You'll need to memorize that. But again, it's easy enough. Just it's products minus reactants. So here is our fourth way of finding delta H. We've done calorimetry. We've done bond enthalpy. We've done Hess's law with the mini equations. In doing formation enthalpies here, by combining the formation numbers in such a fashion, in the background, they have already done what does the formation equation itself look like, and they've already tabulated a bunch of numbers. So again, for the handful of molecules we have here, for the states of chemicals, we have a column full of these enthalpies of formation. Notice they didn't ask you to write out the equation. They didn't say, what is the formation of methane? They didn't say carbon, solid, 2H2, gas, oh, this makes 1 CH4. They've done all that for you, and all they said is, in doing this experimentally, we found that the delta H is 74. And now you're welcome to use that 74. In the background, it relates to this equation. But because of the enthalpy cycle, because these arrows canceled out in such a fashion, because I get from the same start, same finish, I'm going to just imagine in the background, I'm just operating on these numbers here. And in the background, the mini equations are exactly the ones I wanted, and they would cancel in the background. Sort of Hess's law, it's done this part in the background for you, so we just have to do the delta H part. So I'm going to do a practice question with you very shortly. We're going to come back to this table later on to talk about entropy, to talk about Gibbs free energy formation, but for the time being, we're just looking at the enthalpy column. So let's just run our way through a question here. I'm interested in finding the delta H. So example, calculate the delta H for the decomposition of NH4NO3. Okay. This decomposition is a little bit scarier, so I'm just going to give you these values here. NH4NO3. Decomposition, usually full decomposition makes me form elements. In this case here, it doesn't fully decompose. It ends up forming dinitrogen monoxide there, plus 2 waters, right? And they're just interested in, based on the decomposition as written, can you tell me what is the delta H for this reaction? I want to emphasize here, you'll notice this equation is not a formation equation. This equation was not, let's make NH4NO3, let's make water, whatever. What we're going to do is we're going to be able to find the delta H of something that's not a formation equation, but we're going to use the formation way of solving it. Normally, you would be given the enthalpy of formation on table 14. In this case here, because they're ionic, I'm just going to give you these values. You can look these up. Delta H here are just going to be in units kilojoules per mole, like all your enthalpy changes have been so far. The delta H is just going across here, negative 366. This one is positive 82. This one here is negative 286. So just looking at those numbers directly, they've already done a lot of background work for you. They've already written, if I made NH4NO3 from pure nitrogen, hydrogen, and oxygen, if I made 1 mole of it bearing the odd fraction, to create 1 mole, it needs negative 366. We're just going to operate on these numbers by themselves, not really having to do the mini equations ourselves. So, again, here's the emphasis. We are trying to find the delta H here. I'm going to emphasize this is a decomposition reaction. This big equation is not a formation. But what I'm going to choose to do is I'm going to choose to use the formation detour, the formation way to get from the same start to the same finish. If I use formation numbers, our formula is you add up all the formation values of products minus add up all the formation values for reactants. In this case here, even better than bond enthalpy, I'm not having to do Lewis structures, I'm not having to count the bonds or whatever. They've already tabulated a bunch of these delta HFs for you, and all I'm doing here is I'm going to say, okay, on the product side here, I am forming N2O. In the background, I would have been making it from nitrogens and oxygens. I'm going to be forming water. Water here is specified here. This one here is water as a liquid. You're going to need to be careful on the table. Sometimes it's steam, so it's going to be gas. So I'm going to form water. How come there was that little pesky little 1 in the definition? How come I'm interested in making 1 mole? How come I was okay with having the odd fraction here? The reason for it is, in this case, if I know the heat of formation is always quoted for 1, and now my decomposition actually wants to make 2 moles of it, I know Hess's law says you double something, you double the 1 mole value by 1. So it's actually good to have the technical 1 mole in the definition. I'm guaranteed all these table values are for 1 mole. If later on I need to scale it up, I can scale it up pretty easily. So I'm going to minus off here the heat of formation, the gluing together, the making of NH4NO3. Right. And since they've already given you the numbers here, the making of the first one was a positive 82. Making of the second one, even though I had to double it, is a negative 286. That one was exo. We minus off the making of the reactant, negative 366. And voila, we have our delta H here. 82 minus 2 times 286 plus 366. This is going to be the sort of the difficulty of math that we're going to do. Very simple addition, subtraction, right? Products minus reactants, reactants minus products. Just remember minus and negative becomes a positive, but that's about it. In this case here, the delta H here is negative, so make sure you know delta H negative means exo. And if it is exothermic, you want to be able to tell me, well, exo heat term is on the right-hand side. We just calculated here. It's actually going to be a plus 124 kilojoules. It's implied per mole. Every time you run this statement, for every 1 mole NH4NO3 that you want to decompose, you release 124. For every 2 moles of water, you produce 124. If you only produce 1 mole of water, you release half of that. Everything is quoted per mole. So again, I want to emphasize here, you'll notice I was able to find the delta H of something that was totally not a formation. But what I did is I engineered a formation detour around it. I had the same start, same finish. That's what the formula does for you. It doesn't matter whether it's a decomposition. If you take this formation detour, if you do products minus reactants, it gets you from the same start, same finish, and it gives you the overall delta H. One quick aside, and then I'll end off with one last question. So a quick aside here. Let's go back and let's take a look at the formation of oxygen. In fact, it could be the formation of any element. So if I just wanted to write out the formation equation, from what we know from earlier, there's a pesky little 1. It's like balancing where that number can't change. I want to make 1 mole of this compound. in its regular form. So oxygen is diatomic gases. There's many different ways I can form oxygen. Formation requires you to start from the elements. What elements make up oxygen? Hopefully you're able to say, well, oxygen, right? Uh-oh. In this case here, we have O2 becoming O2. Hopefully you're able to say, well, because oxygen is already elemental, oxygen is already as simple as I get. And in this case here, because there is no reaction, it was O2 before, it's still O2, nothing has changed. Because there is no bonds breaking, bonds forming, or whatever, we're going to have the enthalpy of formation. This is written as a formation because I'm making 1 mole from the Lego blocks, from the elements. In fact, the heat of formation for oxygen in this case here is going to be 0. You will not find that on any data booklet, right? Because it assumes you know oxygen is an element. In fact, we can generalize that. We can say the delta HF of any element is actually 0. Now, most people do memorize that. Okay, that's perfectly fine. But they start thinking, okay, enthalpy of element 0, enthalpy of element 0. No, it's only the enthalpy of formation of element 0. Tomorrow when we come back and we do combustion, when you burn elements, probably there's a reaction, probably there's some energy change. But at the very least here, the formation enthalpy that we're doing in this lesson here, formation of any element is 0 because there's no reaction involved. The elements are as simple as we can get it. So I'm just going to do one last problem with you here. Your worksheet will have more these questions here. Let's have a look here. I want you to calculate. So new example. I want you to calculate the enthalpy change. Calculate the delta H. Is it exo overall or endo overall? Calculate the enthalpy change for the following equation. It will look like a combustion equation, although when we come back tomorrow, there's a technical note I want to add. What we're going to do is we're going to look at the burning of ethane. Again, when we do our organic chapter next year, this will become super easy. Hopefully you remember eth means there's 2 carbons. The A and E suffix actually means we're single bonded. So I'm going to take the ethane with 2 carbons. So I'm gonna draw out this molecule for you here. So imagine I have 2 carbons. Every carbon has the equivalent of 4 bonds. So aside from the single bond here, each carbon here has 3 H's. This is getting us a little bit into bond enthalpy we'll see in a second here. So I have ethane there. That's the formula here, C2H6. Right, you can do the 2n plus 2 if you like. We're going to add it to oxygen. Oxygen is a O2. It's actually double bonded in your Lewis structure. We're going to always assume combustion is complete. So we're going to produce CO2 and we're going to produce water. For a combustion reaction, it's best to say water is actually a liquid, but we'll come back to that. CO2 is our double-double, so be really good with Lewis structures. Water here is sort of H2O. It's sort of bent molecule, Mickey Mouse molecule. All right, so we have that there. Remember, for a correct Lewis diagram, you have to have all the dots. Although in this chapter, because we're not necessarily worried about the dots themselves, we're worried about the bond enthalpies, the strength of the bonds, or in this case here, formation enthalpies. Sometimes we're a little sloppy with the dots there. So this is the equation I want. I want you to burn this one here. And in this case here, you'll notice this is not a formation equation. We're doing a burning, right? So in this case here, there's nothing that's fixed to be a 1. I'm going to try to balance this one here. All the carbon here ends up in the CO2. I'm going to try putting a 2 there. 6 hydrogens puts a 3 here. That ends up putting a sort of an odd number of oxygens. Back in our earlier chapter, we would have just scaled it up. Let's pretend we actually double the ethane. In that case there, we actually have 4 CO2. We'll need 6 parts water, 14 oxygen, so I need a 7 there. So although we did talk about formation, it has to be for 1 mole, this equation here is not formation. This equation is just some random equation, turns out to be a burning equation, and they are interested in you finding the delta H for this reaction. Tomorrow this is going to be similar to a delta HC, which is delta H for combustion, but for the time being I just want you to calculate the delta H. This has nothing to do with formation, it's just find out whether this equation, burning, is an X or endo, is the heat term on the left side or the right side. What I'm going to ask you to do, however, is I'm going to ask you try to do it using bond enthalpies. That was one way of doing it. And the other method that we did this time is try to use formation data. Use heats of formation like we just did. We're going to see both ways work, and then we're going to compare which ones do we believe in more. For bond enthalpy here, I already did all the Lewis structures for you. We had to memorize these formulas here. So bond enthalpies. For bond enthalpy, the formula was reactants minus products. while for the formation data that I just did here, formation was products minus reactants. It's important for you to realize here, again, we're going to figure out why it's reactants minus products in the next lesson, but it's important for you to realize when we say delta H, it is always going from reactants to products. So whether in the formulas later on we go reactants minus products or products minus reactants, it is still trying to find out the energy at the end of the day, products minus the energy at the beginning. It's just when we actually operate with different numbers, sometimes our formulas actually switch. So let's try it out with the bond enthalpies here. Bond enthalpies we can find on table 11, while formation enthalpies we're going to find on table 12. In this case here for bond enthalpy, let's just write down all the bonds that we're trying to break here. So sometimes I even say bonds broken minus bonds formed. I would imply the broken part is the reactant side and the formed part is products. What bonds am I trying to rip apart for the ethane? So ethane has 6 C to H bonds, right? CH3s, and I actually need to break 2 times of ethane. So I'm actually going to break on the reactant side. I want to break 12 CH bonds, 6 in one molecule times the 2. I still need to break the carbon-carbon single bond. Each ethane has 1 of them. With the 2 there, I need to break 1 CC single bond. The oxygen only has an OO double bond, and there's 7 of them. So I want to break 7 OO double bonds. I'm going to take that, and I'm going to minus off the bond enthalpies on the product side. Every CO2 has 2 CO single bonds. There's 4 CO2s I want to rip apart. So I want to rip apart 8 C double bond O's. Every water molecule here has 2 OH bonds, and I want to break 6 of them. So in total, I'm going to go 12 OH bonds. Right? Sometimes you're going to find, well, I may have CH bonds on the left and still some CH bonds on the right. You can be clever and cancel out how many CHs on either side, but I find it's easy enough just to do the math that way. So if you can pull out table number 12, table number 11 here for your bond enthalpies. Lots of use of your data booklet in this chapter here. So we're going to take our bond enthalpies, single bond, carbon and hydrogen, double check my numbers. I'm getting 414. Carbon-carbon single bond was 346. OO double bond on the bottom, this one here is 498. CO double bond is 804. And then we have oxygen, hydrogen, this one here, O and H. I'm getting 463. Right, very simple math that we're doing. We're going to take 12 times 414 plus 2 times that. Just type it all in there. Right, you can check my work here. And then we're going to minus off. Careful, this minus here distributes in. So either type this in directly first and then minus it, or minus this term and then minus another term. So just simple math there. Minus 8 times 804, minus 12 times 463. And what I'm getting here is negative 2842. I know the units are going to be kilojoules per mole because everything in the table was kilojoules per mole. What does it mean for delta H to be negative? Hopefully you were to say exo for me here. And in this case here for exo, it means heat is released. It means based on the bond enthalpy method, this one here has released 2842. You'll see that not only is that good practice for the early lesson, it was a lot of work. Really tedious. I had to draw all the Lewis structures. I had to count up how many bonds I'm breaking with these balanced equations. In comparison, it's actually a lot simpler using formation numbers. Formation numbers, the background does all these mini equations and manipulates them for you. All I'm doing is I'm operating the numbers on table number 12. All I'm going to do is I'm going to say, well, I'm going to take 4 times how much the making of CO2 is, plus 6 times the making of H2O, and I'm going to minus off 2 times the formation value of ethane, C2H6, and I'm going to add 7 times the formation value. I didn't even need to use Lewis structures for this. Just make sure you do use the correct table here. Unfortunately for bond enthalpy, I'm going to allude to this later on as well. Bond enthalpy, we had 2 limitations. One was things had to be gaseous. Other reason was things are averaged. That means I had put water in the gas state. Normally when we do a combustion, we're going to see in tomorrow's lesson, back when we're in the standard state, water is usually a liquid. So usually when I look up the water value, I'd use liquid. But in this question only, because I'm trying to make a comparison, which one's better, which one's worse here, I'm going to, just for this problem, I'm going to use up the value for steam, which is water as a gas. On table 12, you actually have this as a liquid or as a gas. To make it a fair comparison, I'm going to use the steam value on both sides. So again, double check my numbers here. 4 times the CO2 value. Formation of CO2 as a gas is negative 393.5. I'm going to use the steam value for water. I'm given water, liquid, water, gas. As a gas, it's negative 241.8, also kilojoules per mole. The ethane molecule as a gas, heat of formation is negative 84. And then, oh no, I can't find this one here on the table. Well, because this is an element here, we know it's 0. You can't form oxygen from anything simpler than that. Crunch through the math there, right? I didn't need to worry about how many bonds or whatever. I'm just operating on these tabulated formation enthalpies. Behind the scenes, there's a lot of, oh, let's make 1 mole of this compound from its pure elements. I'm not having to see any of that detail. I'm not having to do any mini equations and swapping that. And somehow I have the delta H. This big equation was a combustion, but I ended up using the enthalpy formation detour around to get that. First thing you'll notice is these are fairly close, right? In the big scheme of things here, they're both about negative 2800. They're both exo and all that. But why the difference? Well, in this case here, a lot of these formation values are measured experimentally, so that could be a problem. I would actually argue between the two of these, which one can I believe in more? I would probably believe this one here is a little bit more credible. And the reason for that here is back to the notion bond enthalpies have an average. Because I had to look at similar compounds, I had to see sometimes there's electron withdrawing, sometimes there's electron donating kind of principles here, sometimes it's stronger and weaker. Although averages are useful, they can apply to all molecules, they're not specific enough to apply to a single molecule. Whereas when I look at this side, even though I do have some experimental problems, making sure you sort of minimize heat loss to the surroundings, things like that, these ones here are exactly for CO2, for water, for ethane. It's not for a similar compound to ethane. It's for a specific molecule, which is why I believe this one here to be slightly more credible than the bond enthalpy. Again, this is the one strange example that I did, sort of gas for everything. When we come back in tomorrow's lesson to take a look at combustion numbers, we're going to have water generally as a liquid. So make sure you practice your worksheets and let me know if you have any questions. Thanks, guys.